Hi everyone, my name is Dorinda Bassey and I work at Red Hat in the automotive team. With me here is Matej.
Hi, I'm Matej Hrica. I also work in the automotive team.
So in this presentation, we'll be talking about VirtIO GPU and where are we now. So we'll be focusing on implementing the VirtIO GPU device in the Rust-VMM project, and we'll talk about like the problems we faced and how we worked on the device. So just to provide a little bit of introduction, one of our goals for the Red Hat automotive team in the virtualization space is to provide a virtualization solution for the Red Hat in-vehicle operating system. And in order to run Android on top of our virtualization solution for Rivals, we need to satisfy the Android reference platform requirements, which Sergio talked about yesterday in his presentation. And these requirements specify features that are needed for the Android automotive system. So it's a bit outdated, but still the requirements are still valid. So another of our objectives was to allow multiple automotive OSs to coexist by sharing the GPU. And since the VirtIO GPU driver that's in the guest need these VirtIO interfaces to be able to access the GPU on the host, it kind of provides a minimal performance overhead. So just to show you a brief illustration, this is the architecture for running the Android Automotive OS as a guest VM. And the idea is that when the Android Automotive OS is running as a guest without any direct access to the GPU, it could use the open source graphics drivers like Mesa or gfxstream, along with a VirtIO GPU driver and the device to provide the Android guest with an indirect access to the GPU for graphics processing. And this here is our architecture for QEMU KVM as a hardware agnostic hypervisor. So first of all, we have a standalone emulated VirtIO GPU device that's running the host user space. And this device will show up in the guest through the VirtIO GPU PCI bus. It defines how this VirtIO GPU device is exposed to the guest OS. Now, the application that's running the guest can make calls to the VirtIO GPU driver to render these graphics. And a typical example is, let's say, for instance, an application may use OpenGL or I think Vulkan APIs, which are supported by the driver. It would use it to make calls to the driver. And then this device would receive those commands in form of vert queues and translate them into actions that the host GPU can perform. And this is all being sent through the corresponding host libraries and interfaces. In summary, the VirtIO GPU device is a power virtualized graphics device and is based off on the VirtIO specification standard. It's consisting of the PCI device, the driver, and the device itself. And it allows for both 2D and 3D graphics acceleration. And as we continue in this presentation, I would mention these terminologies more often. Okay, so let's go back in history. The interesting thing is we've had a lot of historical developments with VirtIO GPU, and the first development started with the inclusion of the driver 9 years ago by Dave Early and Gerd Hoffman, as this was one of the first steps that was taken towards having this hardware acceleration in the guest VMs. And then around the same time, they added the VirtIO GPU device with the accelerated 2D mode and the PCI proxy that was required for this device to be fully functional. And then moving onward came like more supports for the EDID, the context type initialization, and the UUID, that's the UUID-based resource sharing mechanism, and also the blob resource support. And there are many more developments which I will not highlight here. So where are we now? Many implementations of this device are beginning to exist. Crosvm itself has a VirtIO GPU device, and libkeyron has a VirtIO GPU device as well. QEMU has about 4 VirtIO GPU device variants, and we are currently working towards replacing the vhost-user device version that's in QEMU. We're replacing it with vhost device GPU in the Rust-VMM project. And currently this PR is still open, and the device code is based on libkeyron and the Crosvm VirtIO GPU code base. So We are leveraging on virglrenderer and the gfxstream libraries through the rutabaga crate for the rendering purposes. And I know you're wondering, okay, why did we add the gfxstream component? We added that one because of the Android automotive reference platform. It supports just OpenGL ES and Vulkan. So with this gfxstream rendering mode enabled, we can have this GLES and Vulkan calls forwarded to the host. Another interesting thing about the device that we're currently developing is that it supports the already existing DBus and GTK display. So when this device is used with the DBus display, it would allow for QEMU to send the display information over the DBus system to an external process that's, in our case, we're using Snow Globe. And this would take care of rendering the data to the screen. DBus, although is a bit more complex than the GTK display, but our team is prioritizing using the DBus display because it has a lot of advantages, such as being able to be used in like containerized environments. And in cases where direct access to the display is not readily available, DBus is useful here. And also, our recent developments are based off on the VirtIO 1.2 specification. So why did we decide to implement this device in Rust? There were so many reasons, one of which was that the device crate would allow for compatibility with various VMMs, take for example, QEMU or Crosvm, and it could operate as an independent process separated from QEMU. So the competition for resources between QEMU and the VirtIO GPU device would be minimized, and this would help to reduce the attack surface on QEMU. Another reason was that we could reuse the vhost-user framework dependencies, and it meant that we could benefit from this framework to implement the GPU functionality. There's also the recent PR which we had worked on to add support for the QEMU's vhost-user GPU protocol. And for obvious reasons, the benefits of the Rust language. So here, I want to talk a little bit more about the differences between the existing vhost-user GPU device that's in QEMU and the vhost device GPU that's in the Rust-VMM project. So the main difference is just boils down to these feature bits of VirtIO GPU. For the QEMU C version, it uses virglrenderer, and it has support for virgl 3D mode, the EDID feature, but it seems to be lacking the blob resource support, the context type initialization, and the shared memory region. Whereas for the vhost device GPU that's in Rust, which we're developing, it allows you to switch between two backends, the virglrenderer backend and the gfxstream backend. And it has support for virgl, for EDID, and the context initialization feature. And as I speak, our team is currently working on adding the blob resource support and the host visible features. The related patches to enable it have been submitted to both QEMU and the Rust-VMM vhost crate. So with this inclusion, we should have a fully functional vhost device GPU. And just for reference, I added a link in the slides for this device pull request.
The VirtIO GPU protocol requires the device to specify feature flags it supports. The driver in the guest can then acknowledge and use the ones it wishes to use. The vhost-user protocol is designed to offload the VirtIO device processing from the QEMU process to another user space process running on the host. This user space process is then responsible for implementing the device functionality as per the VirtIO spec of that specific device. There are two sides to the communication: the front end, which is in our case QEMU, which is the hypervisor, and the back end, which is the device itself. In our case, it's the vhost device GPU. The messages are sent over a Unix domain socket, but also a shared memory is established. Implementing the GPU device as a vhost user device requires some GPU specific messages in the protocol. The flow of the messages usually comes from the front end, where it sends them to the back end. But there are some requests we need the back end to request from the front end. So two other sockets are established, the backend request socket and the GPU socket. The backend request socket is in general for more devices. And in our case, we use it to map shared memory regions. There is also the GPU specific socket, and we need that for display output and things related to that, such as updating the cursor location and cursor image. The VirtIO GPU device itself uses two virt queues. Virt queue is basically a queue of buffers located in the guest memory. And the device readable buffers containing the commands are processed by the device, and then the replies are written to writable buffers. Each virt queue consists of three parts: a descriptor table, available ring, and a used ring. The main queue in the VirtIO GPU device is the control queue. It's responsible for handling most of the commands. The commands come in form of requests, such as get display info or get EDID. And the device processes these commands and can return responses that contain the specific display info or the EDID information of the display. There is also the cursor queue, which is separate from the control queue, and it is basically a fast track for cursor commands. This is useful, so when you are moving the cursor doesn't lag behind as it waits for other commands to be processed. The VirtIO specification also has what are called shared memory regions. These allow us to use zero copy operations on some buffers. We need to support these in order to implement Vulkan using Venus, which is the virglrenderer implementation, as well as gfxstream support in general. This requires some changes in QEMU to be able to use this over the vhost protocol, as well as the Rust-VMM vhost framework. The advantage of implementing shared memory support is that in turn we can implement blob resources. Resources, in case of the VirtIO GPU, can reside even in GPU memory, but this depends on the type of the resource and the specific implementation. But when using normal resources, the data has to be copied from the guest memory, which is always the CPU memory, to the resource on the host. And if the device wanted to read the resource back, it has to be copied again. Implementing the shared memory regions allows us to implement blob resources, which have an operation for mapping the resources into the guest memory address space. And so this allows us to transfer data without explicitly copying it.
Okay, so for the device operation, how it works is that we have one worker thread, and when a new request is received, depending on the queue type, we have different handlers for processing the request. So there's a control queue handler and a cursor queue handler, which Matej already talked about the queues. So during the processing of these queues, it uses the reader and writer module of the VirtIO queue crate to iterate over the descriptors. Although when we started working on the device, this wasn't how it used to work, because we would handle this descriptor processing inside of the process queue. But thanks to the recent addition by Matej, we've been able to abstract it into the VirtIO queue crate. So during the processing, the GPU command decoder processing, it decodes the GPU command and uses the Rutabaga interface to process the intermediate representations of these GPU commands. And in the end, a response is sent only after the command processing is complete. So On success, it will send a successful response, or on error to return one of the error codes. So to explain in details the processing of the GPU commands, there are some commands that need to communicate with the front end using the GPU communication socket. And when we're processing commands like the get display info command, what happens is that we're retrieving the display information from the front end through the GPU communication socket, and then we're processing the display modes. And for the flush resource command side, its goal is to take a specific resource and read its data, and then update the associated display with that data. There are other commands here which can be viewed in the PR of the vhost device GPU crate. For the rutabaga component side, what happens is that it can either initialize virglrenderer or the gfxstream backend as a component, and it uses the virglrenderer set flag method. So this specific flag would configure virglrenderer for operating within the rutabaga framework. And it's the virglrenderer backend there would now convert these GPU commands to the OpenGL API calls for rendering. And similarly, like the same thing happens for the gfxstream backend. It would convert it to OpenGL and OpenGL ES and Vulkan API calls, and forward it to the host through the gfxstream libraries. And one thing to add is that the virglrenderer backend can also forward the Vulkan API calls, but this may require like some Vulkan driver setup in the guest. And depending on the distributions, not all guests have that readily available. And this is the Rutabaga Virtual Graphics interface here. It's designed to be portable across various VMMs, and this is why we adopted it as a layer on top of the gfxstream and the virglrenderer in our backend. This VGI here relies on context types to be able to manage the different kinds of GPU commands that are issued from the guest. And these context types are basically different implementations that can handle the graphics commands, such as rendering with different backends. In the coming up talk by Sergio, he's going to discuss more about context. So while we were working on this device, we faced a couple of problems, one of which was that the rutabaga context could only be initialized once. And this was because the rutabaga context itself was tied to a single process. So due to the structure of the vhost device crate, which was different, it requires a vring to have the fence functionality. So one of the solutions we had here was to initialize the context on the first call to the handle event function. Another challenge that we had was that the rutabaga struct couldn't be transferred between threads. So this restriction was also due to the gfxstream and the virglrenderer backend, because they had to be called from the same thread. And it kind of complicated matters as well with the vhost backend, because the vhost backend was using worker threads which could be called from different threads. And the solution here was to use like a thread local storage and stop the process when the guest shuts down. So since there's no way to reset rutabaga without restarting the process, we just stop the process. Although like it's different for the other VirtIO devices that's in the Rust-VMM crate, because the process gets restarted automatically. And the other problem we faced was the rutabaga dependencies on the third-party modules, which by default crates that are distributed through crates.io shouldn't contain these submodule contents. So we're currently discussing with the Crosvm maintainers to actually have this dependence on Git submodules eradicated. So we would now just use the Rust source files and make it easier for other projects to use rutabaga.
Our main focus currently is Android support, and gfxstream seems to be the preferred solution for that. Android actually also supports virglrenderer, but it does not support Venus, which is the Vulkan implementation in virglrenderer. And obviously, we want the more modern Vulkan API to be enabled. There is also the possibility on horizon that the gfxstream could be used on normal Linux guests because a few days ago gfxstream got merged into Mesa. This is the guest side support. So we'll see how that works out. Virtual renderer is more suitable for virtualizing Linux guests currently. It can be used for OpenGL and Vulkan. Though, like I discovered that in Fedora, the Mesa that's built there doesn't ship the Venus driver. Our implementation of the GPU doesn't handle the rendering itself. It offloads that to the gfxstream or virglrenderer libraries, but we still run some benchmarks to ensure that we aren't doing anything slow. And actually, here you can see that when running glmark off screen, which is the second line, that the performance is about the same. But when running it on screen, it's quite a bit slower with the Rust-VMM vhost-user GPU. And this is because we currently don't support like a fast path for the display output. And we could use the same calls in that the QEMU vhost-user GPU uses. But these are not exposed through the Rutabaga GFX interface. So we have to work on that. We also run Android benchmark where we compared 3D Mark Slingshot, gfxstream against the virglrenderer, and it was about the same. But keep in mind this has the same issue where we copy the display output instead of using DMA buff to directly output it to the screen. There is no support for Vulkan in virglrenderer, so we don't really have anything to compare that to. In the future, we are looking into improving the scan-out performance using DMA buffs, so the display output isn't copied, and maybe add support for snapshotting. Currently, virglrenderer and gfxstream are used through Rutabaga GFX, and we thought maybe specific Rust crates could be created for those. Here we have a demo of running Fedora using the vhost-user GPU. We are using the dbus for display output and the snow globe application for actually showing the display. When starting the vhost-user GPU, we configure the socket path and the renderer to use virglrenderer for Fedora. And then we configure the same socket for the GPU when starting QEMU. And we also specify a shared memory region, shared memory size, which is the size of the shared memory regions for mapping the blob resources. Once the guest boots, we can run OpenGL applications such as glmark. And we can also run Vulkan applications using Venus. But when I try to run VKCube, it first uses CPU rendering because the package of Mesa doesn't ship with a Venus driver. So you can override that, and when you build Mesa from source and use the built Venus driver, this works, but it's a bit choppy right now. So it might be probably related to the scan out that's copying the display output, and that slows down the whole pipeline. We can also run Android. Here in Snow Globe, we now enable emulating touch and show host cursor to actually see where the mouse cursor is. And we also started the vhost device GPU, but this time with a gfxstream. We use the start AVM script, where we also specify custom QEMU because of the patches that are not yet upstream. And we can run an Android image. And as you can see, Android boots, and we can run 3D applications. Yeah. But the performance isn't great right now. The benchmark is kind of heavy also, but the main problem is probably the scan out, which is being copied to the CPU. And also the call to copy it is blocking, which might lead to some issues, which we are working on fixing. And that's all. Thank you. Can accept questions.
Okay, thank you. So if you don't have any questions, I have one for you. How many of you use the existing vhost-user GPU that's in QEMU? Okay, I see some hands. So maybe it would be nice if you help us try out the vhost device GPU and leave some feedback. The PR is linked in the slide, I think. Let me show you in this slide. So if you check the KVM forum talk, you would see, you get the link to it. This one. Yes. Thank you.